So when we talk about formula mass, so formula mass is basically the sum of the average of the molecules that you have. Like, so for instance, when we talk about like sodium chloride, so sodium chloride has so sodium chloride is an ionic compound, right? NaCl.
Mm-hmm.
And it's based upon charges. And have you guys played with a whole bunch of magnets?
Yes.
Before?
Yes.
So if you put one magnet and another magnet together, they come together and they attract, right?
Mm-hmm. Yes.
So are they capable of attracting more than that just single magnet?
Yes.
Okay.
Yes.
So sodium chloride is very much the same way, because sodium is a total positive charge. So it's going to be able to attract more than that one chloride. So what happens is they form what we call a lattice. So you'll have sodium chloride, and then on top you'll have a chloride attached to that sodium. On the other side you'll have a chloride attached to that sodium. So it'll look like this. And then in the spaces here, you'd have sodium, right? And so they all attach with each other, you know, so like the chlorides will be interacting with this sodium as well as interacting with the sodium on top here, and as well as interacting with the sodium over here, right? Because chloride is negative, it's going to interact with all of those positive. It isn't going to discriminate, right? So they form what we call a crystalline lattice that way. So formula mass is just the average of that crystalline lattice. And it doesn't make too much of a difference to most people, but as chemists, we want to get to the nitty-gritty and make sure that we understand things the correct way. So when we talk about the formula mass makes reference to just sodium chloride, the sum of the sodium and the chloride ion. So how much does a sodium ion weigh? Does everybody have their periodic table available? Let's see if I have mine.
Sodium's 23.
Okay, so sodium's 23 roughly, so 22.99, and then chloride is what?
35.
Okay, so it's about 35. Okay, so the formula mass would be just the sum of those two, because essentially you're taking the average. So if we have like 50 molecules of sodium and 50 molecules of chlorine, then when we put them all together, we're just going to get that average, and we're going to use that as the mass for that molecule. So that's called your formula mass, okay? And that's mainly done when you're talking about ionic compounds, right? Because it's based solely on charge, okay? So then if we calculate the formula mass for sodium chloride, it's just going to be the sum of the two. So it's going to be that 23 plus our 35. Okay, so the formula mass for sodium chloride would be 58 units. Do you guys get that?
Mm-hmm.
Okay, good. Now, when we're talking about a covalent bond, let's say we're talking about carbon dioxide. So I have CO2. Okay, in this context, these guys are actually bonded to each other. So this would be called, the mass when we calculate this mass would be called the molecular mass. Okay, so for the molecule.
What are you doing?
I'm writing. Am I not supposed to do that?
I'm sorry, I was talking to my daughter.
Oh, okay. Thought I was in trouble. Okay, so we have the molecular mass, right? So again, it's just going to be taking in how many of each one we have. So how many carbons do we have?
1.
And how much does it weigh?
12.0.
Okay, so 12. And then oxygen, how many oxygens do we have?
2.
2.
So we have 2. 2 times, and how much does oxygen weigh?
15.
15 or 16?
Oh, and a 16.
Oh, so it's roughly 16, right? So then we add these two together. So that's what, 32. So what, 40? Can't do too complicated math in my head anymore. My brain starts tapping out around 6. Okay, so that's what, 42?
44.
44. Sorry, 44. Just keeping you on your toes.
Sorry, I count things all day long, so.
Oh, I see. So times 2, because there's 2. Okay.
That's right.
Times 2.
Okay, and so it's going to be 44 units since we're talking about a single molecule of carbon dioxide. Okay, piece of cake. So
Yes.
that's calculating the molecular mass of a compound. Okay, and so formula mass is really, like I said, is mainly for like ionic compounds. And then molecular mass is really for your covalent compounds. Okay, but we will often, and you will see it in the book, and you will see it in literature, where you'll say molecular mass for sodium chloride, or you'll say molecular mass for potassium iodide, which are both ionic compounds. And so we'll often misuse them, but a good chemist knows, like if you're pressed on it, you know the difference, right? You guys get that?
Yeah.
Okay, good. Let's see. Come on. There we go. Okay, so this is just basically showing you what we just talked about. So for instance, if we're looking at chloroform, the chemical formula for chloroform is CHCl3. Okay, so it has how many carbons?
What are we looking at?
1.
Chloroform.
Oh, okay.
That's
1.
So this is the chemical formula for chloroform.
1,
1.
Okay, how many hydrogens?
1.
1,
How many chlorines?
3.
3.
Okay, so to calculate the molecular mass or the molecular weight, again, another word that we will use interchangeably, we would just multiply the mass of the carbon. Carbon weighs 12, hydrogen weighs 1, and the chlorine weighs 35.45. Now, 45.45 is like a pretty decent number. So if we get 3 of them together, they basically add up to 1.5 roughly, right? So we want to make sure that we try to take that in consideration when we're doing that addition. So we just add them all up together, and then that's going to give us our molecular mass. Okay, piece of cake?
Mm-hmm.
Okay, so this here is the molecular formula for aspirin. Okay, so since this is the molecular formula for aspirin, how many carbons are in aspirin?
9.
How many hydrogens?
8.
8.
And how many oxygens?
4.
4.
Okay, so that gives me my quantity of each of those atoms. So if I want to calculate the molecular mass for that, I multiply each of them by their masses. Piece of cake, not too hard.
Okay.
Okay, excellent. Let's see how well you guys do. So let's see, what chemical am I gonna give you? We'll start off simple. Let's do sucrose. Sucrose, chemical formula is C12, H22, O11. Okay. So what am I going to do if I want the molar mass?
And do, say, carbon 12 times 12
There I go. Carbon 12 times 12.
is 24. And then
12
hydrogen,
times 12 is 24.
I'm sorry, 12 times 12?
Yeah,
12 times 12 is 144.
144. Okay.
Yes.
I'm about to say.
Okay,
man.
12 times 2 for some reason.
Oh, don't worry. I'm having one of those days, so I can relate.
And then hydrogen. So since hydrogen is only one, it'd be 22, right?
Yep. So it'd be 1 times 22.
And then oxygen, 11 times 16? Or we're rounding up, right?
11 times 16. Yep.
176.
Thank you. And the average is 242?
Said 242.
Yeah.
Are you sure?
I don't know,
176.
I got 342.
Okay.
Ah, there we go. Oh, yeah. I forgot to carry the one.
Get ahead of myself. Okay, piece of cake, simple, not too hard.
Yeah.
Dr. Henry, I have a cool question.
Okay,
For molecular mass, the AMU's the units, right? So you would put 342 AMU for the molecular mass?
you could put units. AMU actually is atomic mass units. So yeah, you could also use atomic mass units as well.
Okay.
Yep. So again, it's one of those things that varies between books. I mean, you'll see the difference on the two. Kristen, you weren't waiting in the waiting room too long, were you? Okay, so you guys got that pretty simple, not too hard? Yeah, no, maybe?
Yep, I do.
Okay. Okay, so we've already talked about the concept of formula weight, right? And that distinction. So when we're calculating the formula mass, again, it's just going to be the average of the two. We've already talked about sodium chloride. I told you about the lattice, right? Sorry.
Are we able to bring notes tomorrow or anything like that?
Yes, you could bring notes
Bring as
if
much
you want to bring
notes
notes.
as you want? Okay.
Yes, yes, you can.
We need to use a calculator. Are we able to use our phone or do we?
Yes, you're able to use your calculator and you're able to use your phone. I recommend you bring your phone. One of you guys will probably be working with the chemicals and you guys should take turns doing it. And the other one should be recording what the other person is doing. So you guys remember what you did.
Okay.
You know, I like videos. I'm very fond of videos. Subtle hint. Okay, so let's talk about the mole. Oh, sorry, let's finish this. So when we're talking about sodium chloride, right, we know that it's the formula mass that we're looking at, right? And so it's just going to be the average of them. So in this case, we're just going to say that there's one sodium and there's one chloride, and then we're going to use that as a formula mass. Even though we know that it forms this nice little lattice structure. Do you guys get that?
Mhm.
Okay. Okay, so the mole. Okay, so how many eggs are in a dozen of eggs?
12.
12.
How many donuts are in a dozen of donuts?
12.
12.
How many husbands are in a dozen of husbands?
12.
12.
Okay, so we know that a dozen is always going to be,
12.
okay? So regardless of whatever it is, you know it's 12, right?
Mm-hmm.
Okay, so the mole is exactly the same way, right? Only thing, a mole isn't 12. A mole is Avogadro's number. A lot of people say avocado's number, which is 6.022 times 10 to the 23rd.
What is this again, Dr. Henry? What are you writing?
This is Avogadro's number.
Okay.
Okay, so this is what a mole will equal. 1 mole and often we will just write MOL is the abbreviation, but 1 mole equals 6.022 times 10 to the 23rd. Pretty simple. Yeah, no, maybe?
Yes.
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 Okay, so this is also called Avogadro's number. It's on the next slide, so I'll save it for spelling it because I'm going to butcher it, even though I know it's on the next slide. Right? So Avogadro's number, 6.022 times 10 to the 23rd. Can you repeat that for me?
6.22 times 10 to the 23rd.
Okay, that's going to be 1 mole, right? So if I have a mole of husbands, how many husbands do I have?
6.22 times 10 to the 23rd of them.
Okay, so if I have a mole of pennies, how many pennies do I have?
6.022 times 10 to the 23rd.
If I have a mole of dollars, how many dollars do I have?
6.22 times 10 to the 23rd.
Okay,
Yeah.
so you guys know what a mole is, right? And you're not going to forget that ever, right?
Mhm.
So anyway, it's worded, it's still always going to be that, basically.
That's right. Okay, so 1 mole will be that quantity, right? So a mole, like I said, is just like a dozen, right? Only thing is a whole bunch more. Okay, so I'm going to ask you, if I have a mole of pennies, or if I have $1 trillion, which one would you have? Which one would you prefer? A mole of pennies or $1 trillion?
A mole of pennies.
Mole pennies.
Baltazar, how many do you prefer? Which one do you prefer?
I don't know. Probably the more pennies.
A mole of pennies? So is that consensus? Everybody want a mole of pennies?
I don't know, that money sounds good. I'm kidding.
Okay, so $1 trillion. So $1 billion is 10 to the 9th. $1 trillion is 10 to the 12th. Okay, so that's cash money. And a penny, how many pennies will equal $1?
100.
100. So if we just divide this number by 100, we'll get 6.022 times 10 to the 21st dollars. Which one is bigger? 10 to the 12th
10
or
to the 20
6.022 times 10 to the 21st?
1 mole.
1 mole. Yes, 1 mole of pennies would be significantly bigger, right?
Yes.
So you guys get that. You see how much that is relative to everything else?
Yes.
Right? Okay, good. Okay, so this brings us to, what was that?
It's a lot.
Yeah, it is a lot,
Like
right?
one more.
Yeah, I would love to have that in my bank account right now too.
Who wouldn't?
Good point.
You wouldn't be.
Okay, so as we were talking about, the mole basically defines a quantity, a number, an amount, right? And so a mole can be used for many things. We can talk about molecules, we can talk about atoms, we can talk about ions, right? So we can use a mole to sit there and describe all of those things. We can talk about husbands, wives, girlfriends. Now, if you have a mole of husbands or wives, that would be a problem. Way too many.
Not
Just
enough.
Okay.
right there.
That means you just know how to multitask. No, I'm just
Multitask, that would be really some serious multitasking going on there. Okay, so now the thing is that this number is basically going to be equal to a pure carbon-12 isotope. You guys remember the carbon-12 isotope? Yep, nope.
Kind of.
Okay, well, you should. Okay, so 1 mole of carbon is equal to 12 grams. Of carbon, okay? So often when we define our molar mass, when we're talking about substances, and the reason why we want to use a mole, because we've talked about how small an atom is, right? Did we talk about how small an atom is? We talked about the football
Yes.
field and the,
Yeah.
okay? Yeah, so an atom is going to be really, really small, right? And so since we know an atom is going to be really, really small, are you able to sit there and do chemistry with a single atom?
No.
No. So in most cases, we have to do it with quantities that are tangible to us, things that we can feel and touch, right? Otherwise, it's going to be impossible. We'd have to sit under a microscope and, okay, I think I got it in the well there, and hope that they find each other, you know? It's going to be impossible. So we typically use quantities that are large enough for us to work with. 12 grams, wouldn't that be large enough for you to work with?
Yes.
Yeah. Okay. So in that case, we're going to be working on a molar level, on the moles level, right? So then we're going to define the periodic table based upon the mole as well. So we say, if you look on the periodic table, carbon weighs 12 grams per mole. So rather than using AMU, atomic mass units, which is talking about a single carbon atom, we're talking about a mole of carbon. Carbon, 1 mole of carbon weighs 12 grams. So it makes it a little more like it's the scale up, okay? And so the periodic table is designed to be scaled up. So we know that carbon is 12 grams per mole. How many grams per mole is oxygen?
fifth, 16?
16?
16. So 15.9998, right? So you guys get that, right? You understand that?
Yeah.
So
Yeah.
that's why we start using grams per mole, or we can talk about AMUs. So, because it's scalable, okay? And again, the carbon atom is what we start defining our mass based upon. So it kind of works out perfect. Okay. Okay. So we've talked about Avogadro's number, 6 point what?
022 point or 10 to the 23rd times 10
Yep.
to the 23rd.
Times 10 to the 23rd. 6.022 times 10 to the 23rd. Right. So we know that that's going to be 1 mole. So that's going to give us a quantity, right? So 1 mole is going to equal this much, even though we know that 1 mole of carbon weighs this much. Okay. So we know that 12 grams of carbon will be a total of 6.022 times 10 to the 23rd carbon atoms. So in theory, you can calculate how much a single carbon weighs, right? Right? No, yes, no, maybe.
Yes.
Correct. Okay, so you see how we can kind of use this to our advantage? So we know that 1 mole is equal to this value, and we know that 1 mole is also equal to the molar mass of what we're working with. Now, if 1 mole is 6.022 times 10 to the 23rd, and I have a mole of carbon, and I have a mole of oxygen, are they going to weigh the same?
No.
No. Okay, because oxygen weighs different, right?
16. Yes.
16, right? And so if we're talking about oxygen gas, O2, which is when I say oxygen generally, how much would a mole of oxygen gas weigh?
16. Still.
What was it?
Oh. 2 times 2 is 36. 32.
32. So it would be 32 grams per mole. You get it?
Yes.
Good. And this is a great class. Sarah, you know, we should just go out and have a beer. We should do this at a bar. You know, it's just you and I. We don't need anybody else. Nobody else is here anyway. Both. Okay, so we were talking about oxygen being 32 grams per mole, right? Because it's oxygen gas and that's its natural state, right?
Yes.
Yes.
Okay, so you're all good. We're all good. We understand that, right? So if I have a
Yes.
mole of iron, a mole of mercury, and a mole of uranium, are they all going to weigh the same amount? Or is one of them going to weigh more than the other?
One's gonna weigh more.
Which one?
I'm still trying to find him. Wait, iron is.
I'll write them on the board. Hold on. So we have iron. I'll type them. Iron, mercury,
Yeah, iron's 55.8.
and uranium. We were real busy. We were just, you know. Okay, so we have some answers.
Mercury should weigh more.
You said mercury.
Yeah.
Okay.
If it's mercury 1, because you said mercury 1 works as a diatomic, so it's H2.
It's diatomic ion.
Yeah.
Ion.
Yeah, diatomic ion.
So did I say a diatomic ion?
No.
Okay, so you're putting words in my mouth.
Otherwise, it's uranium.
It's uranium. So if we look on a periodic table, right? It should be uranium, right? If I can get to the periodic table. There we go. So uranium is down here, right there. So it would be down in this row right up here. This is mercury. And iron is up here. So uranium is going to weigh more. Okay, you guys get that?
Mm-hmm.
Okay, good. I know it's simple. I just want to be sure that we're all on the same page. Okay, so let me see. Maybe I can get to the next page. So I'm showing you exactly the same thing that we just talked about, right? So these here, this here, all of these compounds, this is showing you what a mole is, right? For each one of those. Does it look the same for all of them?
No.
No.
No. But the funny thing is that they all have exactly the same number of molecules, right? Or atoms, not molecules. So here, this is 1 mole of zinc. It has 6.022 times 10 to the 23rd atoms of zinc. This here is 1 mole of carbon. That has 6.022 times 10 to the 23rd atoms of carbon. Do you guys see that?
Yes.
So even though they look different, right? They're the same quantity there. So quantity-wise, they have exactly the same quantity there, right? So kind of like, let's put this into a perspective of things that we know. Grapes and apples. So I could have 32 grapes, and I could have 32 apples. Which one is going to probably weigh more?
The apples.
The apples, right? They're the same quantity, but the apples are going to weigh more, right? So that's what I'm showing you here. They have exactly the same quantity, but you can tell by the weights that they're different weights, but quantity-wise, they're exactly the same, okay? So now when we do a lot of those stuff that we do in class, do you think we're going to be taking into consideration weight or quantity? Which one would be better to do comparisons?
Quantity.
Quantity,
Weight.
right? You say weight?
I did.
You did? Not quantity?
Well, yeah, well, I would say both. They
So
both
tell me
matter,
about-
I guess.
Tell me about carbon dioxide.
What do
Tell
you
me
want
about
to know?
carbon dioxide. Tell me about it. Just tell me what you want me to know about it. How many carbons are in there?
1.
How many?
So carbon dioxide?
Carbon dioxide.
Is that CO2?
That's CO2. Yes, CO2. So how many carbons?
1 carbon.
1,
1 carbon. How many oxygens?
2.
2.
Okay, so if I have 5 carbon dioxides, what is going to be the ratio of carbon to oxygen?
Can you repeat that?
I said if I have 5 carbon dioxides, what is going to be the ratio of carbon to oxygen?
5 carbons and 10 oxygens.
So if I have 5 carbon dioxides, what is going to be the ratio? So she says 5 carbons. So we're going to have 5 carbons and 10 oxygens.
You have a 5 to 10 ratio.
So a 5 to 10 ratio or a 1 to 2 ratio, the same thing as what we see here,
Mhm.
isn't it? 5 to 10, 1 to 2.
Yeah.
5 to 10, isn't that the same thing as a 1 to 2?
Yes.
Yeah.
Okay, so if I have 1,000,000 carbon dioxides, what is going to be my ratio?
A 1 to 2 still.
It's still going to be 1 to 2. So is that quantity changing between those two?
No.
No. So when we're working with chemical equations, we're going to want to try to use quantity rather than mass, because the mass of a million molecules of carbon dioxide is going to be quite different than 5 molecules of carbon dioxide, right? Although the ratio is going to be the same about the mass roughly, but it's still going to be different. And it's a lot easier to deal with quantity because, 2 to 1, right? Rather than, okay, so let me go ahead and weigh, 5 pounds of carbon dioxide because I only want so much oxygen, right? Do you guys get that?
Yeah.
Let's see. Oh, I got carried away. Okay, so we've talked about molar mass, right? Grams per mole. And I kind of explained to you what it means. Are you feeling comfortable with that? Are you there?
Yes.
So
Yes.
grams
Yeah.
per mole makes reference to our molar mass, right? It's the mass based upon the number of moles. So you're going to see another term called molar volume, right? So what do you think that's going to be based upon?
Volume of the mole.
Volume per mole, right? Okay, so we've talked about the molar mass of the elements. You have a good idea, a good understanding of it. We've talked about the average atomic mass, right? AMU,
Mhm.
Mm-hmm.
okay? So let's see. Let's do this. Let's calculate the molar mass of sulfuric acid. Okay, so how would I calculate the molar mass of this?
Two hydrogens, so it'd be 2 times 1, right?
Okay,
Which is 2.
2 times 1.
And is that sulfur? So sulfur is 32.
Okay,
And then
The
times 1, right?
uh-huh.
Which is 32. And then 4 times 16, which is 64.
Okay. So 64. So let's add that all together. I need to find better
Right.
clear spaces.
98.
You got
98.
so you said 98?
Yeah.
Yes.
98 grams per mole. Piece of cake?
Cake.
Okay. So are you feeling pretty good about this? You understand it? You see how it works out, right?
Yeah.
Okay, good. Okay, so if we want to calculate the number of moles that a particular substance have, then we just divide by the molar mass. Okay? So here's an example. According to the nutritional guidelines, United States Department of Agriculture, according to the nutritional guidelines from the United States Department of Agriculture, the estimate average requirement for dietary potassium is 4.7 grams. What is the estimated average requirement of potassium in moles? So we want to go from grams to moles. So in this case, we're going to be using the mass or the molar mass of potassium. So 4.7 grams, and then that is a horrible line. That line's in the wrong spot. Oops. So then the grams are going to cancel out. and then we're left with only moles. Piece of cake?
Yeah.
Okay, so let me give you guys one. So let's say we calculated the molar mass of sucrose, right? Earlier?
Yeah,
Okay, do you guys remember what it was?
342.
So if I have, let's see, 100 grams of sucrose, how many moles would that be?
Five, 42.
0.3 moles.
Okay, and how did you calculate that?
Do 100 grams of the sucrose times 1 mole, or divided, 1 mole divided by 342 grams.
Okay,
So you did 100 grams times 1 mole divided by 100 grams? Is that what you said?
now he said 1 mole over 342
342.
Yeah, my bad.
grams. So then your grams of sucrose are going to cancel out. And then you're just going to be left with moles of sucrose. That should be 22. Not 12. Okay, piece of cake.
Yeah.
Okay, so again, in this context, we're going to be using dimensional analysis. Yeah. So let's say I have a pound of sucrose. So what would I do differently in that case?
You have a what?
1 pound of sucrose. Because we're in the US, we're talking about sugar.
You have
What
to
was that?
convert the pounds to grams and then do division to grams.
Okay. So we essentially do exactly the same thing, but except for the first thing that we do is convert our pounds into grams.
I would go pounds, kilograms, grams.
So you said pounds, kilograms, grams. So I need more room. That's what you're telling me. Okay, so how many pounds are in a kilogram?
1 pound per 2.2 kilograms? Or is it the other way around?
Oh, you're right. Or no, 2.2 pounds. 2.2 pounds.
Per 1 kilogram.
Yeah. I don't have a printed out copy. I can print one out for you. Give me 1 second. Okay, and then we have grams. Grams to kilograms would be what?
Be
1,000.
Okay. Okay, so then we can cancel out that unit. You can cancel out your pounds. You can cancel your kilograms, grams, grams.
Then you got the mole.
And then we got our number of moles. Piece of cake?
Yes.
Okay, good. Clear. Come on. Okay, so it says a liter of air containing 9.2 times 10 to the minus 4 moles of argon. What is the mass of argon in liters? So in this case, we're going from moles of argon to mass of argon. Again, we're going to be using molar mass. So, but in this case, we're just going to be multiplying it by the molar mass. So we're going to line it up so that our starting number is 9.2 times 10 to the negative 4 moles of argon. And we know the molar mass of argon by looking at the periodic table is what?
Forty?
Okay, so it's going to be roughly 40. So then we just multiply that by 40 and we get 0.037 grams of argon. Okay, piece of cake?
Yeah. I
So
got
now
I
do you
got a
guys-
random question.
Okay,
Do you have like a PDF of a periodic table that I can?
yes, I will have them for you tomorrow. I'm in the process of
Okay.
printing things out, but you're going to have to staple the stuff I give you yourselves because I ran out of staples.
Okay, that's fine.
Okay, or actually, I actually may be able to get it to work. I just got to figure out how to put the machine to work. So that's the next part. Now, what was that?
Is the library going to be open or
No, the library isn't going to be open. Yeah. Okay, so let's say we have 0.05 moles of water. How much does that weigh? Or what is the mass? Okay. So what am I going to do?
Start with the mole of water.
Okay. So we have 0.05.
Mm-hmm.
And what is the chemical formula for water?
H2O.
Okay, so then what am I going to do with that?
Use your molar mass.
Molar mass. So what is the molar mass of water and how do I calculate it?
Molar mass of water is, you have 2 hydrogens times 1
18 grams.
is,
Okay.
yeah, there you go.
1 times 16 is for oxygen.
Mm-hmm.
Okay, so then that's going to be a total of 18 grams per mole. Okay, so I have 18 grams per mole. What am I going to do with that 18 grams per mole?
You are going to use that to times that by the 0.05 moles of H2O. So you have 1 mole on the bottom and then the 18 grams on top.
Okay. And 18 grams on top. Okay, what do you guys get? And how many sig figs should I have? Slacking here.
You should have one,
I should have one.
so it'd just be 0.9, 0.9.
Okay, piece of cake. Okay, so you guys, how do you feel about this? Pretty simple, not too hard?
This right here is a little challenging for me, but you know, I'll keep studying later on, but
It's
seems
just,
pretty fairly simple.
it's just,
Just
the
takes me a
dimensional-
little longer than
Okay.
others.
Okay. It is just the dimensional analysis that you were doing earlier.
Yeah,
And now we're just applying it to chemicals, right?
right.
So here it says, copper is commonly used to fabricate electrical wire. How many copper atoms are in 5.0 grams of copper wire? So here we're going to be going from mass, we're starting with mass, to moles, to the number of atoms, okay? So we know the mass, and we know how to convert the mass. We use the atomic mass, or the molar mass. So then that's going to give me my number of moles. So we have 5.0 grams of copper. We're going to divide it by 1 mole divided by 63.55 grams per mole. And then we know Avogadro's number, which is
6.022 10 to the 23rd power.
okay, simple. So if I wanted to calculate the number of, let's say we have 8.50 grams of neon, and we want to know the number of neon molecules, or neon atoms. Hold on one second. Sorry about that. Little semantics going on with the with housing, so I have to get that taken care of. Okay, so we have 8.01 grams of neon. What are we going to do? And we want the number of neon atoms are in that 8.50 grams of neon.
We first convert the grams of neon to moles.
Okay, so how much does neon weigh?
20.
20 grams.
Okay, so am I going to put that on the bottom or on the top?
Bottom.
Okay,
Yeah.
so 20 grams on bottom of neon. And I have 1 mole on top.
Yes.
Okay, so that's going to let me have number of moles. Grams are going to cancel out. And then,
You convert your moles to your atoms.
okay, and how do I do that?
So 1 mole of neon goes at the bottom,
Okay.
and that equals your 6.022 times 10 to the 23 atoms.
Okay, so what did you guys get?
I got 2.56 times 10 to the 23 atoms.
Okay.
I got 2.56. Yeah.
So 2.56 times 10 to the 26,
Yeah.
I got to the 23.
23.
At 23 now.
Yeah.
Okay, I'm running out of room. Let me 2.56 times 10 to the 23. Okay. Piece of cake.
Yeah.
Okay, so let's see. How can we make this more challenging? Okay, so let's see. Let's do. Okay, so here we have an example where we're working with glycerin. So this is the molecular formula I'm sorry, not glycerin, glycine. This is the molecular formula for glycine. So the question says, our bodies synthesize proteins from amino acids. One of these amino acids is glycine, which has a molecular formula of C2H5O2N. How many moles of glycine molecules are contained in 28.35 grams of glycine? Okay, so in this context, the first thing that we're going to do is do what?
Find the molecular mass.
Calculate the molecular mass. Okay, so here we have the molecular mass essentially calculated for us. Piece of cake.
Mm-hmm.
All right, so and you guys are already comfortable doing that. So let's do a real problem, right? Forget glycine. So let's do, let's see, what can we do? What can we do? Let's do nicotine. Get the chemical formula for nicotine. Okay. Okay, you guys ready for nicotine? So if we have C10, H14, N2. And let's assume that we have 2 grams, 2.00 grams of nicotine. What's going to be the number of moles that is? No, they don't. They have no idea. Okay, guys, I am going to have to cut it short today.